Now, in the previous class, we had a little summing up of the previous class. We started with laminar flow, and we started with the Hagen-Poiseuille's equation, right, and we ended up with equation number 1, and then we also used that was for laminar. For the turbulent flow, that is using the friction factor, and we had come up to another equation, that was equation number 2, right. And in one equation we called it to be Blake-Kozeny equation, which was for the laminar flow, and another was for Burke-Plummer, and that was for the turbulent flow, right. And in both the case, of course, from those equations ultimately we came to a derivation or a relation where we utilized the mass velocity g prime factor, and then in terms of g prime we have come to one point with equation 1 and equation 2, right. Now, we let us start from there what we can do, right. So, if we rewrite a little, that delta p was equal to, for equation 1, delta p was equal to 150 g prime square into delta L by phi s dp over phi s dp rho v prime over 1 minus epsilon into mu into 1 minus epsilon by epsilon cube into 1 by rho. This was for equation 1, and another was delta p equals to 1.75 g prime square into delta L by phi s dp into 1 minus epsilon over epsilon cube into 1 by rho. This we said to be equation 2. Now, if we add these two equations by adding equation 1 and 2, what do we get? We get delta p is equals to 150 g prime square into delta L by phi s dp over phi s dp rho v prime over 1 minus epsilon into mu, right, into 1 minus epsilon by epsilon cube into 1 by rho plus 1.75 g prime square into delta L by phi s dp into 1 minus epsilon by epsilon cube, right, into 1 by rho. So, these two, by adding we get these two equations, I mean the full form, right. Now, if we rewrite or rearrange this equation, then we can say that delta p, we can write this as delta p into this goes up, right. So, delta p into rho by g prime square, right. So, into g prime square into phi s dp over delta L into epsilon cube by 1 minus epsilon, right. This is equals to 150 divided by NRE, right, plus 1.75. 5. How? This here only one thing, if you remember that in NRE definition we had said that was 4 by 6. Now, in 4 by 6, if we neglect this term, then phi s dp rho v prime by 1 minus epsilon into mu is the dv rho by mu for the packed bed NRE, right. For NRE in the packed bed we had seen it was 4 by 6, right, phi s dp rho v prime over 1 minus epsilon into mu. This was for NRE. Now, if we assume or neglect this 4 by 6, then this term we can write to be equal to NRE, right, and this we have brought down to this side delta p, right, g prime square in the denominator, phi s dp in the numerator, delta L in the denominator, this epsilon cube by 1 minus epsilon here, right. So, this is equals to, and this was common because g prime square, which we could have taken in rather we should show you, otherwise it may be I have jumped a step. So, our original was 150 g prime square, right, g prime square divided by into delta L by phi s dp by phi s dp rho v prime 1 minus epsilon to mu, right, 1 minus epsilon by epsilon cube into 1 by rho plus 1.75 g prime square to delta L by phi s dp to 1 minus epsilon by epsilon cube into 1 by rho, right. So, from there if we take that a common of g prime square, which is common in both the cases, delta L by phi s dp, right, into 1 minus epsilon by epsilon cube, right, to 1 by rho. Up to this it is common in both the cases, then it remains 150 over phi s dp rho v prime divided by 1 minus epsilon into mu plus 1.75, right. This is there, we have taken this portion as common, right. We have taken this portion as common like this, right. From this we have taken common, right, and that has come g prime square delta L phi s dp 1 minus epsilon by epsilon cube to 1 by rho. So, remained 150 by phi s dp rho v prime by 1 minus epsilon into mu plus here it remained 1.75. Now, if we divide and rearrange, then only we can write that delta p into or g prime square, let us write this way, g prime square. So, here it is phi s dp by delta L, here it is epsilon cube by 1 minus epsilon, right. So, here it was delta p and this rho went up, right. So, delta p rho by g prime square phi s dp by delta L epsilon cube by 1 minus epsilon. So, this can be made equals to 150 divided by, now we said NRE by definition we had said 4 by 6 phi s dp rho v prime divided by 1 minus epsilon into mu, right. If we just ignore that 4 by 6 is roughly equal to 1, then we can say that this is nothing but NRE. So, 150 over NRE plus 1.75, this is the relation, right. So, in this relation what you see that this side expression, this is epsilon cube, this side expression delta p rho by g prime square phi s dp by delta L, the epsilon cube by 1 minus epsilon, this is equal to 150 by NRE plus 1.75, right. Now, you just think this equation combination when we have done, this was done by one scientist called Ergun, and the equation is known as Ergun's equation. This is known as Ergun's equation. This was developed by adding that equation 1 and equation 2. This was done by Ergun, and according to his name, this is named as Ergun's equation, where both the equations 1 and 2 were added up. Now, you will see one good thing here, that we said that Blake-Kozeny equation was valid for NRE less than 10, and we also said that Barkey-Plummer equation is valid for NRE greater than 1000. So, what about if NRE is within less 10 and 1000? Now, you see this Ergun's equation when you are using both, right, the whole expression you are using, right, then between 10 and 1000 anywhere it is applicable, or even less than 10 greater than 1000 also it is applicable. Only the thing why it is applicable, because you see when NRE is very small, for laminar NRE is very small. So, if NRE is very small, less than 10, then this value comes to be 15 and this is 1.75. So, compared to this value 1.75 can be neglected, right. So, we write for NRE less than 10, right, delta p rho by g prime square into phi s dp over delta L, right, epsilon cube over 1 minus epsilon. This can be written as 150 over 10 if it is less than 10, maximum 10. So, let us take it to be maximum 10. So, less than 10 plus 1.75. So, this is 15 plus 1.75. So, compared to 15, 1.75 is negligible, right. So, for laminar flow, we can neglect the second term 1.75. So, this expression then comes to be delta p rho by g prime square into phi s dp by delta L into epsilon cube by 1 minus epsilon. This is equals to 150 over NRE, and we neglect the term 1.75, right. Then this is valid for NRE less than 10, right. Now, what about the other case? The other case is that when nr is greater than 10, our expression Egun's equation was delta p rho by g prime square phi s dp by delta s delta L epsilon cube by 1 minus epsilon. This is equals to 150 over NRE plus 1.75. So, we have already shown when NRE is less than 10, what is the effect. So, we can come back to the Blake-Cousin equation from the Egun's equation. Egun's equation was that by neglecting the second term 1.75, because compared to 150 by NRE, this value when NRE is very low, this 1.75 can be neglected because this term is high. So, our equation comes to delta p rho by g prime square phi s dp by delta L epsilon cube by 1 minus epsilon 150 by NRE, right. That was valid for NRE less than 10, and this we knew as this equation to be Blake-Cousin, right. So, this is Blake-Cousin equation which we have seen. Now, for the other one, when NRE is very high, greater than 1000, right. If NRE for NRE greater than 1000, what we can say? We can say that when NRE is greater than 1000, then delta p rho by g prime square phi s dp by delta L, right, into epsilon cube by 1 minus epsilon, right. This is equals to 150 by 1000 plus 1.75. So, that means this is 150 by 1000, that is 0.15 plus 1.75. So, compared to 1.75, 1.5 is very low, isn't it? So, it is 1/10 of that. It is compared to 1.75, 0.15 is very low, 0.15 or less than that, as the NRE value will be, it will be 1000 or greater than that. So, when it is 1000 or greater than that, then it will be less than 0.15 or lower value, and we can say that 1.75 is much higher than that 0.175 when NRE value is greater than 1000. So, we can say that compared to 1.75, if we neglect this 0.15, then the equation comes down to delta p rho by g prime square into phi s dp by delta L into epsilon cube by 1 minus epsilon, right. This is equals to 1.75, right, and this is we have seen to be known as Barke-Plummer equation, right. So, from the our equation which we have said to be Egun's equation, we can come down to Barke-Plummer equation, or we can go back to Blake-Cousin equation, right. This fundamental thing if we keep in mind, then keeping or remembering the equation, because this equation is very helpful, particularly that Egun's equation. is very helpful for finding out delta P in any packed bed situation, right. So, for packed bed we have seen, and we can establish that Ergun's equation can predict both for less than 10 NRE or NRE greater than 1000, or if the NRE value lies in between 10 and 1000, then also we can utilize that, right. This we have established and we have seen, right. So, Barke-Plummer and Black-Kozeny, these two equations on combination gives us that Black-Kozeny and rather Ergun's equation, and from Ergun's equation we can also find out the other one, that is by neglecting the two terms we got, right, one expression equal to one term plus another term. So, neglecting one we get to the less than 10 NRE or lower value or laminar flow, that we can see, and we can neglect the other higher term 1.75 compared to that, and compared to the higher term 1.75 was low for laminar flow. So, we neglected 1.75, and for turbulent flow compared to 1.75, this was very low, that is that factor by NRE 150 by NRE was very low. So, we neglected that NRE term in that, and we came back to the Barke-Plummer equation, right. So, if we remember this way, that delta P rho by G square, this is one term, and the dimensional term is phi s dp delta L. So, phi s dp by delta L another term, and third one is the how much void fraction, right. So, epsilon cube by 1 minus epsilon is the third term, if we remember this way, right. So, this was equals to 150 over NRE in general for Ergun's equation plus 1.75, right. So, this we can easily say that this 150 by NRE, when we take this, then it is Black-Kozeny, and when we neglect this 150 by NRE, then it is Barke-Plummer, and when we do not neglect both of them, then it becomes Ergun's equation, right. So, if we have also shown that these three can be derived, this expression we have derived, right. So, we can say that from the very basic that is the equation for, we have said that from the equation which was for pipe flow, that is for the Hagen-Paiseli, right. From the Hagen-Paiseli's equation, we have derived that we have derived Black-Kozeny equation, and we said that this is valid for less than 10, NRE less than 10, right. We also showed from the other, that is when the flow is not laminar, but when the flow is turbulent, then we started with the not from Hagen-Paiseli, but from the frictional pressure factor relation, that delta P 4F, right, 4F rho L by D V square by 2, that this relation we had started with, and from there we came back to Barke-Plummer, and that was valid for NRE greater than 1000. Then the question came, when NRE is less than 10, we have an expression for predicting delta P. When NRE is greater than 1000, we have an expression for predicting delta P, right. But how to express the pressure drop relation when NRE is between 10 and 1000, that is neither it is laminar nor it is turbulent, in between, that is in transition zone, what can be done. So, there we have shown that this also can be done when NRE is less than 10, greater than 1000 or in between, with the help of another equation that was developed by adding these two equations and then rearranging, of course rearranging. That rearrangement was done by them, and ultimately they landed up with these parameters or these these expressions as delta P rho by G prime square, this is 1, phi s dP by delta L, this is another, and epsilon cube by 1 minus epsilon, right. So, we have to keep in mind, one is pressure drop, density and mass velocity, these three factor in one, then the sphericity, then particle size and the length of the bed, and third one is the Voigt's fraction. So, in this way these three terms was connected with 150 by NRE plus 1.75 as the Ergun's equation. So, when we neglected the second term, we came to the first, that is laminar, and when we neglected the first term, we came back to the turbulent. So, when it was in between, then the Ergun's equation also can be used using both of them. Say NRE is greater than 10, but less than 1000, say 500. So, in that 500, it becomes 150 by 500 plus 1.75, right. So, it is what? This goes down and this 15, so it is roughly 1/3, that is 0.33. So, 0.33 or 34, say 0.4 roughly. So, 0.4 and 1.74, 1.75, they are not so big, it is 3-4 times only, right. So, in that case it cannot be neglected. So, that is why this two lies between when NRE is less than 10 or greater than 1000, both or in between, that entire thing can be used by this Ergun's equations. Right. So, today let us stop it here. Thank you.